Hello students. We start the study of signals and system by first understanding what are elementary signals. Elementary signals are the basic signal blocks that are used to form complex signals. What happens to the signal or the elementary signals can help us understand the system. We will basically study two kinds of elementary signals, the continuous time elementary signal and the discrete time elementary signal. Let us look at them one by one. First is the unit step signal u of t. As it is written here, the feature of unit step signal is that it will exist for time t greater than 0, which is written here. It has a value of 1. That is the reason why it is called as a unit step signal, and at all other values it is 0. You can see that I have written t greater than 0 as well as t less than 0. What does happen at t is equal to 0? At t is equal to 0, the signal is changing from 0 to 1. So it does not have any specific value. So we know that for t greater than 1 it is 1. So for t greater than 0 it is 1. As well as for t less than 0 it is 0. In certain textbooks it is written that at t is equal to 0 the value is half, because at t is equal to 0, if you expand this much time, then you will find out that slowly the value is going from a 0 value to a 1 value. So it is going from 0 to 1. So in between it might have passed through a value which is half or 1 by 2 or 0.5. So that is the reason why in certain textbooks it is written like this. But for our case, we will consider that unit step signal is basically having value of 1 at t greater than 0 and 0 at t less than 0, and at t is equal to 0 it is discontinuous. Next we look at the ramp signal. The ramp signal, as you can see, it is called as the ramp signal because it's a sloping line. Either it can slope up with respect to time or it will slope down with respect to time. The equation for the ramp signal is as given here. When we write r of t is equal to at, you must remember that a can either be positive or it can be negative. If it's a positive value, then the curve is going to be having a positive slope, and if a is negative, the line is going to have a negative slope. So whatever is written in front of t or whatever is multiplied with t, that basically forms the slope. It can be either a positive slope or a negative slope. You can try to draw this by putting different values of a and t. For example, if I take a is equal to 2 and t, and now I am asked to write what is a into t or 2t, how will I draw it? You can find out that this is t axis, and at 0, 2 into 0 will give me 0, whereas at t is equal to 1 I will get 1 into 2, which is 2. So at 1 I will get the value 2, so let this be 2. Similarly, at t is equal to 2, suppose if I am going to put value of 2 here, I will get 2 into 2, 4. So I will get some value 4. So you can see that the slope will be basically 4. How do we find out slope? We find out slope by height divided by width. So you can see this one, we got the answer as 4. So this height is 2 and this width is 1. So the slope is 2 by 1, which is basically 2. So the slope is basically 2. Sorry, I had written 4 here previously. So the slope is 2. Now in certain textbooks this is also written as r of t is equal to at into u of t. Basically, when we multiply any signal with u of t, it means that that signal exists only for time t greater than 0. Why? Because u of t exists only from t greater than 0 to positive values. So what will happen is your signal r of t at into u of t can be drawn by a signal which looks like having 0 value before t is equal to 0, and after t is equal to 0 it has a positive slope, or in this case it will have a 0 value before t is equal to 0 and have a negative slope after that. So generally in textbooks it is not written as r of t is equal to at, it is also coming with the u of t. If this is the case, I would always recommend you to go for this wave that I have just now drawn. Next is the discrete time signal of unit step and ramp sequence. As you can see here, in unit step sequence, the word sequence basically means that it is a discrete time signal. So in unit step sequence, the equation is very simple. For n greater than or equal to 0, the value is 1, and for n less than 0, the value is 0. We must very clearly understand the difference between a discrete signal and a continuous time signal. For that, let me explain you in a very simple way. Assume a time signal in which I am taking some reading of some sensor. Suppose the signal looks something like this. I will name that signal x of t. And you can see that it exists for all time period, and it has an amplitude which comes in between this range. It can be even below that or even above that. But what you can generally see is it is happening at each and every instant of time. That's why we call this as continuous time signal. Whereas if I am going to sample this, that means I am only going to take some portion of the signals. For example, at this time I am looking what is the signal, at this time I am looking what is the signal, at this time I am trying to find out what is the signal, then here, then here, then here, here. As you can see that I am taking the values of the same continuous time signal in regular intervals. In between these two, I am not taking any signal, I am only taking a signal here. So let us say that the period in which I am going to take the signal is t seconds. That means at every t seconds I am going to take the signal sample. So I took it at 0, I took it at t, then I took it at 2t, then I took it at 3t, capital T, then I took it at 4t, like that it will keep on going. Similarly, previous to 0, I might have taken it at minus t, minus 2t, minus 3t, like that it will go. Now, as you can see, the t is always being written. What we consider in discrete time is we will not take the value of t, we will only write what is in front of t. So I will get 0, 1, 2, 3, 4, like that it will go. Similarly in the negative direction, minus 1, minus 2, minus 3. And this is now not named as t, but now we name it with an integer n. And that is the continuous time signal. Sorry, it is the discrete time signal, this one. So the discrete time signal will always have this particular structure. It will be only existing at times which is given by the integer value. So 0, 1, 2, 3, 4, 5. What is the value in between? In between the values are all 0. We don't care. We are not interested in that. We are only interested in at this specific time what is the values. So this is the discrete time signal. Now coming back to our sequence, as you can see, it is the unit step signal itself which has been sampled like this. And now we are having the signal existing from 0 to 1, 3, 2, 3, 4, 5, all the way up to infinity. And for negative values, its value is all going to be 0. In sequence format, the signal can also be written like this, wherein generally I would say that these are all 0 values and this is all 1 value. So I can basically write 0, 0, 0. I'll put a dot here. So let me write it more neatly. So I will put dots here, then I will say 0, 0, 0. Like that, finally I will reach 1 and then it is totally 1. But how do I understand where is the 0 axis? Where is the time t is equal to 0? For understanding that time period, I will put the arrow. So as you can see, it starts at 0. So I will put an arrow here which is represented by this. So whenever in a sequence you see an arrow, you must understand that this arrow represents n is equal to 0. Similarly, when we are talking of a ramp sequence, we know that there is a ramp straight line. It can be either a positive ramp or a negative ramp. And if I am going to take the discrete samples of that, I will get a signal like this. As you can see here, we can write a signal like R of n is equal to an, where a will basically decide what is going to be the slope. The a can be a positive, which will give me a positive rising signal, or it can be negative, which will give me a signal which is having a negative slope. As I had explained in previous slides, R of n in certain textbooks can also be written as an into u of n. This means that the signal will not exist before 0. So before 0, all its values will be 0, and from 0 it will have this particular part of the signal or this particular part of the signal, which I will now draw it as this. So it means that the signal R of n exists only from n greater than 0. So like that, the signal can be represented using these equations. Let us move to the next elementary signal. Another very important signal is an impulse function. As you can see from this particular diagram, the impulse function only exists at time t is equal to 0. At all other values, its value is basically 0. So what is the value, or what is the height of the signal, or what is the amplitude of the signal at t is equal to 0? You can see that I have just drawn it as an arrow. That means I have drawn it as an arrow. Why? Why am I not giving a particular value to the signal? For understanding that, have a look here. Generally, I am having a pulse. A pulse will exist from some negative time period to some positive time period. Let me take this as 0, and let us assume that this width is tau. And I am going to say that the area under this particular curve is going to be 1. If that is the case, then one thing is sure, that the height must be 1 by tau. Now suppose I am going to squeeze this particular pulse. That means I am going to take these two ends and I am going to squeeze them. If I am trying to squeeze them and I try to maintain the area 1 itself, then what will happen is that the height of the signal will increase. So now I will have a signal which looks like this. This also has a height, but its width will ensure that the area is always 1. Like that, if I further squeeze it, I will get even a further thin pulse, but its height will again increase. Like that, if I keep on squeezing it such that the value of tau extends towards infinity, towards 0, it extends towards 0, then you will find out that the height will basically, which is given by 1 by tau, as tau tends towards infinity, you can say that 1 by tau tends towards infinity. So it is only tending towards infinity, because you can never have a signal that exists exactly having a width of 0, because that cannot be there. Similarly, the height cannot approach infinity. So generally it is an approximation of a very thin pulse which is having a width which is approximately close to 0, and because of which the height is almost very large. But one thing is sure, that the area under that curve will still be equal to 1, and that is what is meant by this particular definition of impulse function, which is also called as a Dirac delta function and written as delta of t, delta of t, delta t. So you can see that if you take the integration of any curve means area of the curve. So this is basically area. So if you take the integration of delta t, you will get the value 1. And for all other values, the value of delta t is equal to 0. This is the definition. Always remember, this definition is the only definition that you should use for impulse function. Otherwise, if you are going to say that a delta t has a value infinity at t equal to 0, and at other values its value is equal to 0, this statement may be correct, but this statement cannot be told to be exactly true. So no need to define it in this way. What you should define is that the area under the impulse function is always 1 and its value is 0 for t not equal to 0. Now, why is a delta function very important? As I had drawn previously, that a continuous time signal can be converted into a discrete time signal, and in discrete time signal, if you remember, I had drawn these samples. So these sample signals are actually the Dirac delta function or the impulse function. That's why this is important. And there are some important properties of impulse function which we need to know. For example, if you multiply any signal with the delta function and take its integration, its value will be the signal value at x is x of 0. This is basically the sampling theorem, not theorem, this is basically the sampling process. Sampling theorem is different. So this is the sampling process. So what I have done, so if suppose there is an axis and there is a signal, let me draw the signal. Suppose there is a signal like this, and I am going to multiply this with an impulse function. The impulse function is existing only at t is equal to 0. Then mathematically what this says is that if you are going to multiply both of this and take an integration, its value will be the value of the signal at x is equal to 0. That means what it says is that the total what you will have in the end is that a signal that exists only at t is equal to 0, and its height is exactly the same height of the signal, or the value of the signal at t is equal to 0. At all other times it is going to be 0, and this is basically the sample of the signal, at t is equal to 0, at small t is equal to 0. So this signal you have sampled at this particular point, t is equal to 0, and that value is here. Now if you take another impulse signal and you not have it at 0, but you shift it slightly in this side so that you have another impulse signal which is here, then you will have a second sample of this particular signal, and that second sample will have this height. So if I am going to draw that, I will draw something like this. Like that I will get. So if this is delta of t, then what is this? This is a shifted signal, which I will say that it has moved back, which I will write it as delta t minus some t naught, where t naught is the gap between these two. You might be asking, sir, how this will become minus and all those things. You will understand when we study signal processing. But anyway, you understand that if we are having some time, we can either subtract some quantity out of it, or we can add some quantity out of it. Based on this, the signal may move either this side, or it may do this side. If it's a negative, then it will move this side. If it's a positive, it will move the left side. But anyway, that will come later. So this is what is basically happening in the process of sampling. So that is what we have written here. The same process is again repeated here. If you can see that if I multiply any signal with delta t, it's as good as multiplying the value of the signal at x0 into delta t. Or if I am having any shifted signal, any shifted impulse, and I am multiplying it with x of t, it is as good as having the value of xt0, which is basically the value at this particular point t0. So I have taken my signal x of t and I have multiplied it with this xt minus t0. So I have got a sample value which is basically x of t0, and that is what is basically written here in this second equation. So these two will basically help us in understanding the sampling process. Another thing is basically delta t. If you take the image of it, it is the same. I mean, the mirror image of it is the same. That means whatever happens in the positive axis is happening in the negative axis. Similarly, this fact we will study later in time scaling. Now let us look at the discrete time sequence of an impulse function. As you can see here, a unit impulse function is a very simple signal which has a value at n is equal to 0, it has a value 1, and at all other times its value is 0. So you can see at all other times its value is 0, at n is equal to 0 it has a value 1. Because of the 1, it is called as a unit impulse sequence. As I already told, sequence means it's a discrete time signal. And just like we had some properties of delta t, we have some properties of delta n. That is, if you multiply a delta n signal with xn, you will get the value of x of 0. Similarly, if you multiply the value of delta n minus n naught, that is a shifted delta signal, with xn, we will get the value of the the value of the signal at a shifted time of n naught, that is this time. And this one is similar, that whatever is happening in the right hand side is the same thing that is happening in the left hand side, which is given by this. As you can see, delta n can be written with respect to this operation where you are taking a un of signal. Un of signal, you all know, is basically like this, which exists from 0 onwards. Whereas if you are going to take a signal which is un minus naught, it is basically shifted back. So at 0 its value is 0, and at other times, that is 1, 2, 3, 4, its value is all 1. Like that it will move forward. Now if you subtract both these signals, you can see that this will cancel out, all these pulses will cancel out with each other. What will only remain is this single pulse, and that is what is delta n. So delta n can also be written as this form. This is something that you will understand after signal sequence. So with this much, we will stop in the part of the elementary signals. In the second part of the elementary signal, we will see slightly more complex signals. Thank you.